you would be right to go to pre-cal. We can give you a little short thing to just see if you got the kind of skills you would need. In the end, you can do whatever you want. You know, in this class, if you go to guide and say, I want to take pre-cal next year, they'll put you in pre-cal next year. I mean, they won't stop you. I mean, it is supposed to be a logical follow-on class. So what we're doing this time, it's called normal distributions. And a lot of this stuff, you know, won't make sense before we go over it, but it'll make sense when we look at it at the end. So the first thing we start with, let's see, I don't even remember what I did here. The science of statistics, right, is how we use that to try to understand the world. And this is what I mean. If, for example, I wanted to know what is the average height of everybody in Hampton, I mean, I could go out there and I could measure every one of them, and I could take the average and I would know what they are, right? But that's probably not practical. So in statistics, you don't go out and measure everybody for whatever thing you're trying to measure. You figure out how you could come up with a smaller sample and find the average of those. And then you kind of infer that that represents the whole population. Now, how well you approximated the actual height of everybody in Hampton depends on how you took your sample and what did you do with it. But that's everything that you study in a statistics class. How can you learn something about the world by studying smaller samples? I mean, even, you know what the census is, right? The census every 10 years, they go out and count these things. I mean, that's actually trying to, when you count everything, that's called a census. But we don't do that very often. You know, most of the time we take smaller samples and we just try to extrapolate to say, oh, if that's the average for that smaller group, let's just say that's the average for everybody. I mean, take, for example, on an election. You know, everybody wants to know who's going to vote on election day and who's going to vote for who. So you see all these polls, right? And the polls are going out there. They're not testing everybody that's going to vote on election day. They don't even know that. But they try to figure out in a smaller group that they'll ask and say, looks like 50% want this person and 40% want that person. Now, is that what's going to happen? Sometimes they're pretty accurate, and sometimes they're not very accurate. If you know what if I knew the average height, if I actually knew the average height of everybody in Hampton, I could take that average. That would be called a parameter of the population. When you don't know it and you just try to figure it out by looking at a smaller group, that is called a statistic. A statistic is when you're just looking at the smaller set and trying to figure out the bigger world by looking at that. So, you know, how accurate is our statistic? Depends on how we collected the data. What do we do with it? I mean, usually after you've collected data, you try to draw a graph of it in some way. And you've done other kinds of graphs. You've done stem and leaf, box and whisker, right? Those are things you did in Algebra 1. This particular kind of graph is called a histogram. In a histogram, you go out and measure everybody. This is people's heights in centimeters. And then this is anybody's height who was between 149.5 and 159.5. You put a little X right there. And then you keep doing that until you've counted everybody and you've put everybody's X in the appropriate bin. And then you could draw rectangles to show how high did that go. And that kind of gives you an idea. I mean, where are the most people's heights? In this bin right here. You know, there's a lot less over here. So we look at data, we look at them in different ways. Histogram is just one. We're not going to be making histograms in here, but drawing graphs is a big part of statistics. Right, here's another histogram, results of an exam. And you can see they've got it in bands of 10. And the number of students who scored in each band, you know, drives the height of the rectangle that way. And you can see the general shape is, it looks like most people scored in this band, and then it's less to this side than it is to this side, right? I mean, there's a longer tail that way than there is this side. So generally, you collect data, you're going to look at a graph, and if you're a statistician of some type, you're looking at three things. You're looking at the shape of the graph. You're looking at the center, because the center probably represents the average, the mean kind of thing. And you're looking for how much is it spread out, right? Shape, center, and spread. Now, you already know center, right? You've done center before. What are the different ways you measure the center of a bunch of data? Mean, median, mode, right? That's assumed that you know what those three are, right? What is the mean? Yeah, it's what we would think of as the average. You add them up, divide by how many. What is the median? The middle, right? Like you throw out the low and the high, the low and the high, the low and the high until there's something in the middle. It's that middle data point, if there is one. If there's two, then you take the average of those two. And then what is the mode? The one that shows up the most, right? So if, if the most people, there was more people that were 70 inches tall than anything else, that's the mode. So mean, median, and mode. We're really only interested for what we're doing today in the mean, the average. That's all we care about. And when it comes to measures of how data is spread out, then there's a few different ways to do that. The one that you probably don't know, I'm not sure how much they go into Algebra 1, is called standard deviation, and that's the one we do. We need to know a little bit about that before we go to normal distribution. The range of data, what is the range of a data set? That's the average. It's the highest minus the lowest, the max minus the min, right? That is a measure of spread. And then there's another one, I'm not sure whether you did, it was called IQR, interquartile range, where you do the Q1, Q2, Q3 thing. We're not doing that now either. All we care about are mean and standard deviation. And again, remember that I said that it's different for the population as it is for the sample. And they actually use different variables to represent these things. And in the book and on the SOL formula sheet, they use different things. You just kind of have to know what they're referring to. They use them incorrectly, by the way. They do use them incorrectly. So, and even your calculator's got them in a different way, which is not really correct either. But usually you use this Greek symbol here, which looks like a U, kind of a fancy U. That goes by the name of mu, right? How can you spell mu? Mu, right? And that letter is standard deviation. That is a Greek letter, sigma. I know how to say that one. Sigma. We use the capital letter sigma when we did our summation. That's the lowercase letter sigma. So that's usually what you look for if you know the population, mean, and standard deviation. All right. When you're dealing with just a sample, usually you're going to use for the sample X with a bar on the top of it, and you say X bar, X bar. Right. If you, for the sample, the standard deviation is a lowercase letter s. Generally, for a population and for models, you use Greek letters. For samples, you use the Roman, our basic alphabet in one form or another. That's the general rule. So we're going to see all these things. Well, we don't see the S here. We should, but we don't. We'll see the rest of them. And I wouldn't get too hung up about whether they use mu or X bar. It means the mean, right? That's the mean. And standard deviation, sigma. Sometimes people will abbreviate standard deviation, SD. Okay. So these are two very basic sets of data, right? What would you say is the mean of these 5 data points? I mean, every one is 3, so what's the mean? 3. Right? I don't need to add those up and divide. It's 3. So I would say that the X bar equals 3. Okay, now, if I want to know how much something is spread out, I would subtract the data point minus the mean. Right? Well, in this case, the x minus x bar is going to be minus 3, minus 3, minus 3, minus 3, minus 3. And in every one of those, it's 0. So if I wanted to know on average, how much is this data spread out? I mean, it's 0. It's not spread out at all. Now look at this one. 1, 2, 3, 4, 5. What would be the mean of those 5 data values? I mean, you can add them up and divide if you want. 1 plus 2 plus 3 plus 4 plus 5 is, what is it? You add them up, you get 15. You divide by 5, you get 3. So this has the same mean as this, but is it the same data? No, because this is not spread out at all, and this looks like it's spread out, right? All the values are not clustered around the mean. So we still have x bar as 3, but when I do the x minus x bar, then minus 3, minus 3, minus 3, minus 3, minus 3. Right, 1 minus 3, negative 2. 2 minus 3, negative 1. 0, 1, and 2. If I added all those up to take the average, what would I get? Yeah, negative 2 plus negative 1 plus 0 plus 1 plus 2. The negative 2 would cancel the positive 2. The negative 1 would cancel the positive 1. If I just took the average of what you would call the deviations, they would cancel each other out and look the same as that. So in statistics, they don't just take the average of those things. Okay? They square them first. Because what happens when you square a negative number? It becomes positive. So that we don't cancel out all of our deviations, we square them, and we're going to get 4 plus 1 plus 0 plus 1 plus 4. Now, what do you get if you add up those? You know, that is, I'm going to put it over here, 10. Now, that's the sum of the squared deviations. If I wanted to know the average of those numbers, what would I do? What is the average of those numbers added up? I would divide by 5. So the average of the squared deviations is 2. But I'm not interested in the squared deviations. I need to know the actual deviations, right? So if this is some measure of the deviation squared, then I would need to do that. I would need to take a square root. Now, that leads to a complicated formula that nobody actually does anymore. Not even AP statistics do they sit around calculating the standard deviation, right? That's the formula for it. In the end, we will put that in the calculator and let the calculator do that part. I mean, you can see it's the square root of, and we know because we just did the sequence and series, what this symbol there does. That's a summation symbol. What it's telling us to do is, the index is I. It says I equals 1 to n, which is going to be how many different data points that we've got. And for each one, we subtract the data value minus the mean, and we square it. And we add them up, and then we divide by how many there were. That's what we just did. And then we take the square root so that it's of the same scale as the numbers that we're trying to find the deviation of. Now, let me hand you... No, I didn't even... No, I'm not going to give this yet. Yeah, I was just noticing, they don't even put this on the formula sheet. I mean, there's no expectation that you would have to use this formula. Okay, this is how we're going to do it. Okay, we're going to put it in the calculator, and we put it in the calculator the same way we've put data in the calculator before. Before we did it to do scatter plots. Right? You remember how did we put the data in the calculator to do a scatter plot? Not in the y equals. Stat. And then the edit is the first column, right? And you're going to put those numbers under L1. So if I do the, let's start with the 3. This one right here. 3, 3, 3, 3, 3. 3, 3, 3, 3, 3. Stat, edit, right? So you enter the data under L1. Okay, then we're going to do stat calc 1. So after these are in there, go stat, arrow over to this calc right here, and 1 for one variable statistics. Enter. And you can see the X bar is given right there. There's the mean. And the one that you're looking for, for the standard deviation, in the calculator, that is a little Greek letter sigma there, that last one, and an X that comes afterwards. I mean, it's only in the calculator you're going to see it listed that way. But so you're looking for X bar and the little sigma X, mean, standard deviation. And you can see the standard deviation is 0. It's not spread out at all, right? It's the same number every time. Now, try to do the same thing with 1, 2, 3, 4, 5 and see where it's different, right? Stat, edit, 1, 2, 3, 4, 5. Right, so you put those in and then do the stat calc 1, stat calc 1. And you could see the mean is still, X bar is 3. And you go down to the sigma X, and it's 1.4. Which, if you remember, when we added up all of our squared deviations and divided by 5, what did we get? Right? When I added them all up and I divided by 5, I got 2. And then take the square root of that. Take the square root of 2 and see what you get. Compare it to this sigma X. It's the same thing, right? So that is the math that went behind them calculating this. And actually, I said that we won't see S, the lowercase letter s for standard deviation, but that is what this is right here. That's SX. And that would be for a sample. But that's the only place you're going to see that until you take AP statistics, and then you're going to see it all the time. Okay, so we understand how to do it in the calculator, and here's the homework. This is page 715, 6 through 9. It's here. If you don't have your book, just look at it right here. Do mean and standard deviation. For now, then we're going to go on. So we haven't talked about normal distribution yet. We're just figuring out what we mean by standard deviation, the normal distribution. Right, just put them in the calculator one at a time. That's the way? Yes. Okay. You'll need the formula sheet later, not for this. Don't worry about variance. Variance is the sum of the squareds divided by 5. It's before you take the square root. That is technically the variance, but we don't need that for normal distribution. Okay. There's like none left. Okay. Yeah. If you in the calculator, let's see. Yeah, they don't have the variance in there. They got the sum of the squares. but they don't have the variance. But if you have the standard deviation, you square it. There's the variance. What's that? There's two I don't have from you.
Yes.
The page 575.
This is not holiday. Because I didn't come. Because this is.
Okay.
Yeah, and I was in SIPs.
Right. This is the one I thought I was just checking. What was the one I just checked before that? What was that? That was the 591. That was the time before. Okay. How about the 575 and 584? That's right. Because you never show me that. Got it. Okay. We about done? Hurry up. Chop, chop. Chop, chop. Right? You guys texting all the time. This should be nothing for you, right? Oh, that's right. We got an extra 5 minutes, don't we? Well, that's like a vacation. What's that? No, mean, standard deviation. Which are the two you look for? The mean is the x bar, standard deviation is sigma x.
So we just write those two.
That doesn't look very right, though. 258?
No, for number 6, don't look right? I typed in all the numbers.
Oh, I can't see it from here. Is that right? Okay. Okay, you're right.
So it is right?
Probably. I can't see it from here. Oh, for number 6? Yeah, those are not big numbers. Yeah.
So what is the answer?
Again, you're looking for the x bar is the mean, and the sigma x is standard deviation. Done. Well, if you want to think of it like that, that's fine, but it's the sigma x.
So that's in that.
Those are the only two things you're looking for. Right? Right? The only things you're looking for are the x bar is the mean, and you're supposed to know that's the mean, and the sigma x, which is standard deviation. That's it. You don't need any of the numbers in between. Did you finish? Okay. 8.7, 42.8, looks good. Thank you. About done, Antoinette? Find me the data. That looks good. How do you do what?
Oh, no, actually, you delete it. There's a blank space.
Did you get them? What's the last one? Looks good. You know, in the terminology here, each one of these data values is represented by an x. X means an individual data value. Sometimes xi is an index. So x1, x2, x3, x4, kind of like a sequence that we did before. We about done? Okay, we don't have all day. Okay. So you already knew about measures of center, mean, median, mode, right? Measures of spread, that's the one. The one that we didn't talk about, shape. Okay. Now, a normal distribution is one particular shape. We're not interested in anything else other than whatever is the shape of a normal distribution. Right. So if you're looking at a histogram, you expect, if it's a normal distribution, that in statistics talk, you would say unimodal, meaning it has one peak, and symmetric. So it should be pretty much the same on one side as the other. Okay? This would be an example of a unimodal and symmetric. I mean, it's not exact on the left and the right, but it's pretty good. I mean, statistics are never going to be perfect, right? There's always a little bit of variation there. So this would be an example of unimodal because it has one peak, and symmetric because it looks the same on the left as it does on the right. They're mirror images of each other, right? Would that be unimodal and symmetric? No. So that is not a, that could not be a normal distribution. That could be. Okay. Now, normally distributed data, things that, again, you go out and measure, and then you make a histogram by putting the values into bins and drawing rectangles. If it has that kind of a shape, it's usually the result of something kind of random going on. Now the book gave these as particular examples. Height, they're always using height, but a lot of times if you're going to give an example of height, then you probably want to split it up between males and females, right? Because they don't have the same height. I mean, if you looked at height for all together, you'd probably come up with a distribution that looks something like that. There'd be a peak for girls, there'd be a peak for boys. That's not unimodal, right? That would not be normal. Weight, I mean, generally these are things that they're the mean, the most people are like right in the middle, and then it falls away to either side, somewhat the same. Test results. I mean, test results of a good test. I mean, if it's an easy test and everybody gets 100, then it's going to look like that, right? Or if it's a really hard test and everybody gets near 0, then it's going to be like that. But if it's like the SAT, which is really controlled well, you're going to see that the maximum is at 500, and then it falls away to either side. In fact, the shape, I think I've got it here. This shape is considered to be like a bell. It's a bell curve. Did I put that there? I didn't put that there. Bell curve. Now, what's here is you can see that there's actual data and histograms in the background, and then this bell curve or normal curve is superimposed on the top, and you can see that it's not exact, right? And in the real world, the data is never going to perfectly fit any kind of model, but it is approximately okay. Now, have any of you taken psych or AP psych or something like that? I know that Miss Persico likes to go off on the book, The Bell Curve, which is obviously there's a normal curve on the front of it because this was written in the early 90s and it tends to make a lot of statements about averages of people's capabilities that some people find racist or unfair or something like that. So that book is generally not considered to be a positive book, but I read it. Had to know what was in it. I was in stats. So. Okay. Now, the thing about, if we just look at the bell curve itself, now no data in the background, but just the optimal bell curve. There's an equation that guides this thing here, right? I think I might have told you the other day about when you find the sum of an arithmetic sequence that there was a famous German mathematician that there's some story about how he came up with that formula. But he's also the one that came up with a mathematical equation for that bell curve. His name is Gauss. And the thing is, since it's pretty much a fixed shape, what we know is that if the mean is the center of the distribution, then you expect in between one standard deviation to the left and one standard deviation to the right, you should have 68% of the data. Right? I mean, you are putting this thing in the bins and that you would expect 68% of your population is falling in between one standard deviation to the left and one standard deviation to the right. And if you spread that out even further, if you know the standard deviation, which we know how to get now, if you go between 2 and -2, then it's 95% of the population. And if you go even further, between 3 and -3, 99.7% of a normally distributed population should fall between -3 and +3 standard deviations. And mostly what you study in statistics is you're looking for unusual data. And normally what you define as being unusual is a data value that falls more than 2 standard deviations from the mean. So if I was measuring somebody's height and I measured something that was over here, I would say, well, that's unusual. If it's in between -2 and 2, say that's expected. If I had a normally distributed population and I drew a sample that had a mean somewhere in there, I'd say, well, that sounds normal. It's within normal ranges. If I got something that was over here, I would say, that's not normal. I better reconsider what I thought was my mean, because that's just too far away to think that I should have gotten that. I mean, it's possible, but that is a lot of what you study in statistics. I would say the second half of the class is all trying to come up with what's unusual and what's not unusual based on a normal distribution, an expected normal distribution. This could go by different names. The empirical rule, the 68, 95, 99.7 rule. So this is an example of a bell curve model. It's a model, right? It's not the actual data. And you could tell that because it's this nice smooth thing instead of all the choppy rectangles in the background. Said the heights of adult American males are approximately normally distributed with the mean, which is right in the middle, of 69.5 and a standard deviation of 2.5. So they've drawn the bell curve and they've labeled the mean there, and they added one standard deviation to the right and another standard deviation and then another, and the same thing to the left. And remember, we said that it was 68% between -1 and +1 standard deviations. So if you break that up, it's going to be exactly symmetric, right? It'll be 34 to the left, 34 to the right. That's what you expect, right? We expect 95% to be in between the 64.5 and the 74.5. Well, if you take away the 68% and divide by 2, that gives you the 13.5 and 13.5. And you could do the same thing and figure out this 2.35 and 2.35. Now, does that add up? Does this plus this plus this plus this plus this plus this, does all that add up to 100%? No, because there's always a little bit in the tail. There is area underneath that graph and above the x-axis. There's a little. I mean, we know it's 99.7% in between here and here. That's not all. There's the 0.3% which is left. So, and then there always will be some teeny little bit that's left there. So what percent of American males are between 67 and 74.5 inches? Okay, well, there's 67 and there's 74.5. So what percent are in between there? Add up the individual percentages. 34 plus 34 plus 13.5. 68 plus 13.5. 81.5%. Right? So, I mean, if you have this kind of diagram, you should be able to answer all of those, right? What percent are in between 64.5 and 69.5? That would be these two, 47.5. Right? As long as you know those basic percentages, which do not change. right? What percent would you expect to be taller than 6 feet, which is 72 inches? So what percent is it that's to the right? 13.5 plus 2.35. And there's actually a little bit more out there. I mean, you could consider that to be, there was 34, 13.5, and to the right of this, just keep going, is 2.5%. So taller than 72, 13.5 plus 2.5, 16%. 16%. Right? Now, normally when you get these problems, it may not give you a diagram. You're expected to draw the diagram. And you could draw, as sloppy of a bell curve as you want. And some people do. I've seen these things look like that. It's okay as long as you divide it up into all those areas. It really won't matter how pretty your graph is. But if you really want to be pretty about it, then you go like this, right? The mean isn't there. You draw your bell curve, something like that. Right, there's the mean. And then it's usually one standard deviation is like halfway down the side of the bell. So like if I go to about right there, that ought to be the one standard deviation to the right. And then that ought to go the same the other side. Right, that's the +1. That's the -1 sigma. And then if I just take the same distance now, there's the 2 plus 2 plus 3. Right, this would be -2 -3. But again, if you want to draw it like that, by all means, you could do it. Okay, so on this one, we're saying the scores on an Algebra 2 final exam are normally distributed with a mean of 150 and a standard deviation of 15. So one standard deviation to the right would be 165, 180, 195. One standard deviation to the left would be 135, 120, and 105. So first step is draw the picture. Second step, try to answer the questions. What percentage of the students who took the score scored above 180? Let's see. We knew that this was the 34, this was the 13.5, and this essentially going this way is 2.5%. So what percent were above 180? 2.5%. Now, they can ask you two kinds of questions like this. They could say what percent is above a certain amount, but if they ask you how many, then you got to know, well, how many people are involved here? In this case, it was 250. So how do you find 2.5% of 250? $250 times 0.025. Right, you multiply by the decimal percent. And what is that? That should be 6.25. Go ahead and do it, Nate. 6.25. So you would expect 6 to 7 might have scored above 135. So remember, that's a different question if they ask what percent are above a certain level, or how many. And if the question is how many, you got to know, what's the total group that took the test. Okay. And let's see. I'm going to skip over that. And to say, you don't have to remember those percentages. The calculator does this for you also. Okay. So this is how you do the normal distribution calculations in the calculator. And if you look at your calculator, it's not going to look the same as mine. Yours is better than this thing that's on the screen, right? But these are the steps. You go second vars. Where's the vars key? Yeah, right there, right? So you're going to go second vars, and there's two normals there, but you want the second one. Second vars 2. You never use the 1. Nobody ever uses the 1, right? We use the 2. Now, you see something like this, right? It says lower, upper, mu, and sigma. So you have to fill in 4 things. If I want to know what percent is between -1 and +1 standard deviations, okay, then the lower is the one on the left. Sorry, that shouldn't have been right. I should have said. The lower is always to the left, and the upper is to the right. Okay, so let's say I'm doing this is called standard normal because the mean is 0 and the standard deviations either side. The lower I'm going to say is -1. The upper is +1. The mean, according to that, is 0, and the standard deviation is 1. Right? So you would enter all that data and then go down to the paste. Keep entering. You know, when it goes down to the paste, you hit enter twice. Right? The first time you hit it, you know, you're going to get normal CDF and it'll have all those numbers filled in parentheses. Mine skips the step of showing this, but yours has that, so you don't have to remember what goes where. And then when you hit enter again, it should give you a decimal percent. And what is it? 0.68. What do we say? What percent of the data falls between -1 and +1? 68%. There you go. You don't have to remember those numbers. You could actually figure it out with a calculator. What did we say was the percent that fell between -2 and +2? 95%. So go back and do the same thing, right? Put in -2 and +2 and see what decimal percentage you get. You know, what it's really doing is finding the area under the curve. Assuming that the whole area is 100%, this is the decimal percent. What did you get? Should be 0.95, 95%. So those percentages, you can actually figure them out. If you don't remember them, it doesn't matter. You can figure them out. But at that point, you're not likely to use those percentages as you are just to go to the calculator, put in the appropriate lower bound, upper bound, mean, and standard deviation, do your calculation. Okay. So for example, same graph, right, where you have the mean of 69.5, the standard deviation is 2.5. If I want to know what percent of the males are less than 66 inches tall, well, notice that 66 is not one of these numbers. It's not exactly 1 standard deviation or 2 standard deviations from the mean. We're talking about, we want the area under the graph here. Right, there's the 66. So in the calculator, when you have this kind of thing where you're finding the lower is, I mean, this goes on infinitely. Usually you just put some number which is really low. I mean, you could put in 0. Right? Because there is no end to this on the left side. So for lower, put in 0. For upper, put in 66. Right? For the mean, mu, put in 69.5. And for the standard deviation, you put in 2.5. And calculate the percent, which is under the graph. What did you get as a percent? What'd you get? 0.08, so 8%. Did everybody get that? 8%? Okay. So then we try to do the same thing. No, I'm not going to do that. What about what percent is more than 70? Okay, 70, again, is not exactly at one of these dashed lines. There's the 70. So for 70, right, we would say the lower is 70 because that's the left side. For the upper, because that goes on forever to the right, you know, you just put in some number that's pretty high. I mean, you could put in 1 million if you want, but it probably 100 would be fine because we'd be so many standard deviations away. There's not much left. 100. The mean is 69.5, and the standard deviation is 2.5. And what percent did you get? 0.42, so 42%. Okay, or if you want to go in between two fixed numbers, like 68 and 73, neither one of which is on your graph. There's 68, there's 73. So the lower will be 68, the upper will be 73, the mean is still 69.5, and the standard deviation is 2.5. What percent did we get? 0.61? 0.64? So 0.64, which is 64%. So in the end, if you have to do a normal distribution calculation, even if it does happen to be at one of these fixed standard deviations, just use the calculator. If you know how to do this thing right there, you'll get them all right, at least as terms of the percent goes. Okay? If they ask you for the number, then they must have given you like the total number that you're choosing from. And there's only one other thing I'm going to say, which is if we look at the, we don't have time for that. If we look at the objectives here, it talks about something called z-scores, which this book barely mentions at all. And we'll get a chance to look at it more when we prepare for the SOL. But the bottom line is the z-score is the number of standard deviations a data value is from the mean. So like in this one here, if the mean is 15.7 and the standard deviation was 2.8, it looks like, yeah, 2.8. Then this value here has a z-score of 1. It means it's 1 standard deviation from the mean. This is 2 standard deviations, 2. These are z-scores. And it's a way to try to quantify how unusual something is by putting what's the z-score. Where minus means it's less than the mean, plus means it's more than the mean. And if you look at the formula sheet that I gave you, you've got that formula right there. For z-score, that's what it's about, right? The x is the data value, the mu is the mean, the sigma is the standard deviation. Okay, so we're going to do our quiz now on arithmetic and geometric. So notice that, let me stop this. I'm not going to assign any more homework, okay? So you're done with homework for today. And